In 2002, there were some experiments carried out in Norway where they actually built embankments on a rock ledge between two reservoirs that were almost prototype in size, 40 meters wide and about 6 meters high. The whole group of people went out there with the intent to make predictions in advance of an experiment of overtopping of one of the embankments. And so my predictions were made using my depth average flow model. So here you see a finite volume mesh draped over the embankment. And there are the embankment parameters. So there's a picture of the embankment itself being overtopped. Normally when embankments are overtopped, there's some sort of head cut that forms on the downstream slope, usually near the toe. The head cut works its way back upstream to the crest and then finally breaks through and you have a huge outflow.
Hello, and welcome to today's webinar on advances in dam breach assessment. It's a hugely important topic in today's world where we've got aging dams and increasing development that would be potentially affected by the failure of those dams. I'm your host, Craig Price, with the International Water Training Institute, and on behalf of the Australian Water School, we are pleased to have you with us. So let's welcome our presenters and panelists today. We've got Tim, Mayari, Monty, David, Kyle. Let us know where you're joining us from and how long you've been in the dam breach business. Let's start with Tim.
I'm joining you from Melbourne in Australia, and I think I did my first dam break analysis back in probably about 1996. So I've been going at it ever since then.
All right, sounds good. Mayari.
Hi, I'm Mayari. I'm from Montreal. It's been, I think, like 4 years in Atkins-Riannis, and in the research, I'm 7 years, let's say.
All right. Monty.
Hi, everyone. I'm from Melbourne as well, but currently in the Middle East. So it's 3:30 a.m. now, but I'm here to, be here.
We appreciate the sacrifice joining us at the late hour. David, likewise.
Yeah, I'm David Froehlich. At the moment, I'm in Pakistan, and so I've been interested in dam breaches and dam flood modeling for a while. The topic of my dissertation was dam breach flood modeling, so it's been a while.
Perfect. Kyle, let's welcome Kyle. Kyle's the one who set this whole thing up and got the topics arranged for us. Kyle,
there's emotion, so I think some of our audience might be familiar with me as the CFD modeler. So I've done quite a bit of bridges, dams, fishways. In the last few years, I've been working with Monty to try, this was the right way of putting it, establish better practices, at least internally, or help deliver assessments and understand how to do these dam breach models a little bit better. So I had a question asked from a client quite a few years back. Can you perform a comprehensive assessment and leave no stone unturned? And I engaged Monty. We started doing more research. We tried to use machine learning and go through various papers and databases and improve things. And all we ended up doing was confusing ourselves a whole lot more. So I guess later on we started to engage Tim, and we discussed with David a bit and tried to understand how we can, I guess, take the knowledge of the academics and the scientists and all the historical stuff and how we can turn it into engineering and end up getting a good outcome. It's a big process, and I hope we can end up educating everyone at the end of the day.
Yes, and
hear from the experts.
With a 60-minute time frame, what we've got basically, and we may have our Q&A run past that, but we try to get you as much as we can out of that comprehensive set of data that and assessment and approaches that we're looking at, and try to get you the best information. What I'll do here is share a couple of additional resources that we've got for you, recognizing that we are not going to be able to even touch the surface of, a comprehensive dam breach analysis and everything that goes into it, but we can provide you with the resources and the links to be able to get you along that way. So if you go to hydroschool.org/breach, I have got a couple of websites that I've set up here with all of the Australian Water School resources that we've covered related to dam breach in the past. So we've got today's webinar. I'll post the recording here. We also have an upcoming course, which is going to be a little more comprehensive, a couple of hours worth with some of the same presenters you see today. You can go ahead and sign up for that even today. It's already available to sign up for. That'll be in June. The registration links are here, and we'll provide those to you in the end. We will also, for those interested in tailings dams specifically, cover the tailings dam topic in some webinars and courses later on this year. This one starts in August. And then we've also got some resources here for you from our previous dam breach assessments with Bill Syme from Tuflo, Chris Goodell, and these are some additional webinars related to dam breach that are already available for you to go back and watch. And in the meantime, since we did this webinar, unfortunately, there have been a number of worldwide dam breach events, some of them fatal. And, this is it's a topic that just keeps, is going to keep us busy going forward to try to prevent some of the risks and assess some of these risks and consequences going forward. If you are interested in deliberate dam removals, so that is technically a dam breach, but typically a little more methodically, we've got a ton of resources for you on dam breaches with the sediment impacts with Stanford Gibson over at the Corps of Engineers, and a bunch of other papers and resources and materials. These are the ones that have been, with deliberate drawdowns to get a dam removed. We also have natural dam breaks, and we'll have another webinar coming up this year on the Earth's biggest floods, most of which were caused by either failures of glaciers, glacial outburst floods, and landslide dams. So that's a very interesting topic when you start looking at paleohydrology, PMFs, a whole bunch of resources for you available here as well. So in the background, with the content that we give you today, keep in mind there will be some additional webinars and courses coming up where we can get into more detail. So with that, David, if you wouldn't mind sharing your screen, David Froehlich, if you are familiar, if anybody watching this webinar is familiar with any dam breach mechanisms and approaches and models, you would have heard of the Froehlich approaches and the equations. So I wanted to have you just share your screen and walk us through a little bit some of the regression equations and your process for analyzing these things, and then we'll move into the other presentations.
So that's to give a brief overview of some of the contributions I've made over the years on this topic. So let me begin with a paper that I was presented in the Journal of Hydraulic Engineering in 2008 titled Embankment Dam Breach Parameters and Our Uncertainties. So as the title should make perfectly clear, the analysis applies only to embankment dams, and this trapezoidal breach model that is often used, it's coded into most of the computer programs people apply, not only predicting these parameters, but also the uncertainties of these parameters, so that hopefully one can take into account the variability of the predictions that come about from dam breach flood modeling. And in this paper, the equations are presented for how to calculate the parameters, the uncertainties, and then there's an application that shows you how to do that. But let me also mention that all of these predictions are based on collected data that I've assembled over the years. These are data that I find reliable. They're just not some numbers that are pulled out of the air or some newspaper article that says the breach width was about 100 meters. No, these are all data that I have documentation for, so I have confidence in them. Of course, they're not perfect, but it's the best available. So later on, after collecting some more data, and realizing that Monte Carlo simulations involving, say, 10,000 realizations or simulations is a little challenging, there's a simpler way to take into account the variability of the outcome, and that's using a point estimation method. And so that's covered in this conference paper that was presented in one of the ASCE Water Resources conferences. So in this paper, which Chris Goodell helped out with by running a bunch of HEC RAS models, we looked at 4 parameters, the 3 breach parameters, the width, the side slope, and the formation time, as well as the discharge coefficient of the weir, or the breach. And this requires 16 runs. So you just make some permutations. You can do that in a few hours. Anyway, so have a look at that paper if you like. Over the years, continuing to collect data as they come about, I updated the nonlinear regression models for these 3 breach parameters and presented that in a paper in Riverflow, pardon me, in 2016. Along the way, a missing piece of information that went into the predictions was the width of the embankment. Suppose you have two embankment dams, and the crest width of one is, say, 4 meters, and another one is 8 meters, and everything else is the same. One would expect that the breach parameters would be different. And finally, with enough data, I was able to determine through these nonlinear models what the effect of this breach width would be. So in this paper, I present 2 sets of equations, one that includes the breach width or the embankment width, and another one that doesn't. The simpler equations are not quite as accurate, but they're simpler, and the uncertainties are also calculated in this paper. So have a look at that. As data become available, I continue to look at things from time to time, and recently I've been looking at the use of neural networks to make predictions of the trapezoidal breach model parameters, and this is a paper that will be presented at the 2024 Riverflow conference in Liverpool. Hasn't been published yet, and I have a journal article that's on the way. So, but the neural networks provide better predictions than the nonlinear models, but one needs to be very careful about applying neural networks, because with these nonlinear regression models, you can easily see how the parameters are extrapolated beyond the limits of the data that were used to develop the formulas. But with neural networks, it's not so. You could easily, if you're extrapolating beyond the limits of the data that were used to develop the neural networks, you could be predicting some nonsense. So one needs to be very careful and run profile traces, but potentially you could have much more accurate results. So we've only been talking about embankment dams that are made of earth and rock fill, but there are other dams that are made of concrete and masonry, and I've collected data for those as well, but there aren't many available. But what little sense I could make of it is shown here. It's a little formula for the average breach width. So these are these concrete dams, and there's a whole variety of things. They could fail by, if it's a massive concrete structure formed with blocks, different sections, they could fail by sliding or overtopping. If it's an arch dam that's relatively thin, it could actually explode, fail almost instantly, such as the well-known Malpasset failure. So, but that's all I know about that. Finally, I want to say, these are all empirical models we've been talking about for this trapezoidal breach formation, but you could also carry out a more causal analysis using a numerical model. And here, in 2002, now I'm going back a ways, there were some tests or experiments carried out in Norway where they actually built embankments on a rock ledge between 2 reservoirs that were almost prototype in size, 40 meters wide and about 6 meters high. And so there was a test carried out in 2002. The whole group of people went out there with the intent to make predictions in advance of an experiment of overtopping of one of the embankments. And so my predictions were made using my depth average flow model. So here you see a finite volume mesh draped over the embankment, and there are the embankment parameters. Let's see here. So there's a picture of the embankment itself being overtopped. Normally when embankments are overtopped, there's some sort of a head cut that forms on the downstream slope, usually near the toe. The head cut works its way back upstream to the crest, and then finally breaks through, and you have a huge outflow. So there's the result of my simulation. You can see the embankment eroding away over time. There, we'll just let it go for a few seconds. And that's enough. You get the idea. So that worked out pretty well. There's a plot of cross sections along the center line of the embankment as a function of time. It took about 2 hours for this embankment to fail, and that's basically my predictions are pretty good. They're not perfect, but they're relatively close, and so the model worked pretty well. And so that's the end of my contributions up to today.
Perfect. Let's have Mayuri start sharing her screen. Thanks so much for that, David. Honored to have you with us, and I'm sure there'll be a lot of questions for you in the Q&A. So go ahead. Let's keep all the presenters engaged. So Mayuri, I can see your screen just fine. Over to you.
So I'm Mayuri from the Water Power and Dam teams of Atkins Realis, and today I'll be presenting a standardized dam breach and assessment approach. So overall, here's the plan of the presentation. I will start with an introduction of uncertainties and the dam breach regulation. After that, I'll be covering a review of dam breach framework around the world. And after that, highlighting the problematic. After that, providing a methodology, so the standardized approach that might help the regulators in the next years, following with a results discussion and conclusion. So first, let's start with dam breach assessment. So uncertainty, as most of you know here, there's various kind of uncertainties related to the dam breach assessment or dam safety study, which overall can be classified into different kinds. So I don't go into all the details, but classifying to hydrological uncertainties, hydraulic uncertainties, knowledge uncertainties, human. In this presentation, we focus on dam breach parameters, uncertainties, but of course it only represents the tip of the iceberg, knowing that in fact the quantification and combination of all those uncertainties will be discussed in a few years and will be very interesting, let's say it like that. So regarding the dam breach regulation currently available, it is interesting to highlight that the current regulation tries to frame through the dam classification, hydrological uncertainties, hydraulic and operational uncertainties. So through the classification, you will have your scenario of design, also has your investigation visit defined. But however, they don't yet include the dam breach uncertainties related to the dam breach parameter, which are in practice defined using guidelines or framework. Overall, it's not a lack of intention, knowing that the dam breach scenario defines the flood plain downstream the dam, but it can be understood through the dam breach models chronology that I will present after. So overall, a brief review of the dam breach framework. It's overall, so the standardized dam breach scenario is defined using 3 failure parameters that overall represent the dam breach shape, so trapezoidal, rectangular, and so through the dimension of the final breach and the slope of the final breach, also has with the dam breach formation time. These allows engineers in practice to compute a standardized dam breach hydrograph, which is route downstream the dam to obtain the floodplain map. So here's a brief review of worldwide, international framework. So through Quebec and different other countries, it is has presented in this table. All are the same, providing the 3 different failure parameters, which are defined depending on the dam type, so concrete dam or embankment dam, knowing that the failure process is different depending on the dam type. So for a concrete dam, it's more instantaneous, so it's more easy to capture and easy to capture the uncertainties related to the failure versus an embankment dam, which is a progressive failure with a lot of limit of knowledge, but so where the uncertainties are higher. So the problematic is that the specification provided in most of current standards refer on historical dam failure, but the real problem is that the accuracy of the specification is directly related to the number of historical dam failure available. So in that perspective, it is why I here choose to present a probabilistic strategy approach, standardized, that helps to identify the controlling dam breach parameters in a dam breach study, define a range of possible dam breach parameter based on historical dam failure case study, but moreover, that allows to quantify uncertainties on the dam breach parameters on the dam failure hydrograph. And in a future perspective, to, if possible, verify or validate these specification using a deterministic dam breach parameter. So overall, here's the dam breach model chronology that I love to present in parallel with the computer history. Here, it's only a brief and exhaustive portrait. So overall, as we noticed, the laptop and flat screen appears only in 1995, which explain the limit or the limited amount of previous model available in dam breach. So empirical, we have a few appearing, and deterministic model also some appearing, but are all overall limited to the computational capacity and the historical dam failure case study available. So it is after, on Froehlich So in 2016, which provide a new database after the one of 1998, which was used to set almost all the standard available. So after after that, regarding the limit of knowledge, this is why after that a group of the various countries went to Norway and developed the impact project, which David just speak about a few seconds ago, and which have led to, I think, like 6 or 7 deterministic model and various paper regarding the deterministic model. And this is why in the literature we see a lot of deterministic model appear through those years, but also regarding this limit of knowledge, why we see parametric models, so simplified modelization of the evolutive failure of an embankment dam appear. And so nowadays we see more and more probabilistic models, some that I will present today, but also artificial model, which refer to the AI method, has presented by Froehlich a few seconds ago. But all of these are still linked to the historical dam failure available. So this is where all my research start. So what was the dam failure case study available? And this is where I end up with by doing a lot of research. It's a very exhaustive and tremendous work, but I did it. So in 2020, I published my database regarding 361 worldwide historical dam failure of all types, so natural, tailing, man-made, of various type, various dam failure. And this is where I start realizing that there's a lot of data there, and we need to set some standard into the registration of those dam failure. So overall, the standardized probabilistic approach referred to historical dam failure. It doesn't really, probabilistic model use doesn't really matter. It's really more the strategy. So overall, it's based on historical dam failures that we use to fit a distribution, so a probabilistic fit, to generate a random dam failure scenario. that we run into a deterministic dam failure model, so parametric, or to traduce the failure hydrograph. We run these random scenarios for 1 million iteration, and for various Monte Carlo runs. So, for example, 100 iteration and 10 Monte Carlo run. Using the latest run, we are able to finally, based on the peak outflow, set or obtain these probabilistic dam breach hydrograph. So overall, there's a proa breach, which I have developed in my PhD, but there's also MEG breach, which can be coupled with ECAS. Most of engineering practice knows ECAS. So here's a few results for the run. Few results provided with the proba breach. So here, and some probabilistic hydrograph. The main discussion remains for me, but for all, I guess, that what is the influence of dam breach parameters. So maybe sometimes we don't need to set a fit distribution or generate various scenarios for some dam breach parameters. But also, what is the fit distribution that we will consider in those types of study? We'll, in the literature, again, here we are not, we haven't decided, let's say, but also the number of Monte Carlo run to consider, and the number of simulation in it, which type of deterministic model that we want to consider. All of that is will need to be studied over the years, but also think in a way that in that standardized approach, knowing that it takes a lot of time in running. So for engineering practice, we need to keep thinking about it. So overall, in conclusion, all this is to improve, of course, flood maps, and eventually be able to, whatever the probabilistic models that we will be using, and regard the influence of the dam breach parameters, to be able to provide probabilistic flood mapping in order to maybe eventually be able to collaborate with insurance companies and see how we can manage all that, these emergency plan better. So here's all my reference about the papers I have published. So the review of the database, my program, and various other papers I published related to the topic. Here the reference for the presentation itself, and I thank you.
Thanks so much. That is a wealth of information. We will try to post as many of those on the accompanying website as we can get up there. Thanks for that. Mari will move into the background and address your audience questions about the technical content. Monty, if you want to start sharing your screen, we're going to hear a little bit more about some of the uncertainties and some new tools. So over to you. I can see your screen just fine if you want to put that into full screen mode.
Fantastic. Two great presentation. Let's see. Here I'm going to focus on the recent advances in breaching parameter model. So I will start with a brief background on the main breaching components, and then I will go through some details of the methods to estimate breaching parameters. Here, the main aim is to focus on the recently developed empirical equation and modeling packages. In terms of the empirical equation, I will elaborate on the outcome of our research on data fusion-based approach. And in terms of the modeling package, I'm going to go through the details, some details of the recently developed modeling package, which called Breacher, developed by Forward Hydro, and then at the end, some conclusion and recommendation. Estimating dam breaching parameters are a challenging task, and the main reason is, as you hear now, there are limited reliable recorded information and data sets, and even with the cases that there are some information, we are not really sure that they are fully reliable. People have go and measure, we rely on them, but there are some level of data set failures. there are complex relationship between different items from the geotechnical side of things to the hydraulic side of things. So that's why if you look into the literature, you see that there is very high level of uncertainty in the literature recorded. So it goes from the 0.5 to 1 order of the magnitude. So that's why when we have this level of the uncertainties and all of these items, we are preparing something and we're sending to a public service. There are times that public service, they are not 100% sure about what we are sending to them. They are looking for more information or more level of the certainties. So if you look into the literature, and if you're just clustering all the models that have been used, so we can just put them in the 4 main categories: physical laboratories, computational fluid dynamics or CFDs, machine learning, and empirical equations. So if we have those, and then we just give some scores based on the complexity, accuracy, user-friendly to the end, which is the cost and purchase, we will see that, yes, for example, in the physical and laboratory, you will get more accuracy. However, you need to deal with at the high level of the complexity, or you need to pay money. You need to people go and do things, build the things, and deal with all of those type of things. When you're coming from those to the machine learnings and models like Monte Carlo or artificial neural network or general expressions, you will get less cost. However, you need to ensure that you understand and you setting the parameter and assumption correctly. For example, for Monte Carlo that we talk, it's very sensitive to distribution selected for each parameters. And in the real life with existing small samples, extracting such a distributions, you cannot be 100% sure. So if someone selects a distribution based on their parameter, for example, say, I will go for the default of normal distribution as a default, then it can significantly impact the outcome. So this issue is similar for the hydrology, for the model that we're on Monte Carlo for the hydrology as well. So we should know that what kind of the distribution we are using, if they are correct or not, we understand. And if we are not 100% sure, then we may substitute those type of things with the other methods like bootstrappings for black box. So yeah, exactly as David just mentioned. So you don't have a fully clear vision or fully control on the relationship. The selection and number of the hidden layers, neurons, objective function, all of those brings more than enough complexity to the exercise. So, and you may not have a good understanding of physical relationship between those. That's why when you look into the literature, you will find out that, okay, between all of those empirical equations seem that they are the optimums. So we see that still they are in the optimum based on those criteria. So that's why they are the most common approaches, honestly, still by today. So generally, any modeling package or spreadsheet-based model that are based on empirical equation, or we can call it like EEs, can be recognized as a good method or reliable method. At least we can call it as a fit for purpose for daily practices and projects. I'm not going through all of these details. It's already mentioned. So there are 3 main breaching parameters: failure times, we have a final breaching width, and the most important one that we are using there for the flood assessment is breaching peak outcomes. The main challenges and shortcomings for empirical equations is limited data that we talked and other person mentions. And most of those required data are for the small dams, usually for dams with a height less than 15. So you need to have a good understanding of the failure mode that you're choosing and why it happens. You need to have a good understanding and information about dam types, what type of the dams you are working. It's very, very, very important to know about these geotechnical characteristics. You need to understand what that erodibility means. You need to have go and have a chat with those geotechnical people. You need to know if any additional safety component has added or not. And then all of these can add some level of uncertainties to the situation. It's not just clicking and using the equation. You need to understand and bring those information and just cook together. So our motivation behind that method was low complexity, low uncertainties, bringing accuracy of machine learning with the simplicity of the empirical equation, and then go through the subjective approach to objective approach. So regardless of experience, you should be able to easily follow the steps at this point initial assessments. Why data fusion approach? If you are dealing with a phenomenon that is a complex or multi-aspects, just using and considering one single element or method is not sufficient, and sometimes it's not correct. So if you go have a chat with your GP that say that, okay, I have something, and if your GP just decide everything based on that conversation, there are many cases that is not enough. So and that needs go and do the blood testing and other things, and they bring all together, reach to the level of the this decision. Similarly, this is the same case for the Danbridge and consequence assessment. It's a complex exercise. You need to have all information. You need to bring people from the multidisciplinary teams and add all of those information together and reach to the level of the confidence. So the steps for data fusion based was we gathered the information. We used the recorded information, which was the literature reviews that they have been already published and they have been properly cited. We fill the gaps. Initial assessment of me is filtering just filtering those cases of observed data that we wasn't really sure that we can use it. They are not really reliable enough. Then we go to say that, okay, we have this number of dams with this type of information, we can use them for example, these breaching parameters. If you look here, you see that there are, for a peak outflow, there are two groups. It's group 1, group 2. The reason is two different groups have been created, honestly, for peak outflow based on the fact that the average width of the embankment is available or not. And this parameter is very, very important. So more reliable equation was just developed recently, or I can say when I said recently, after maybe 2000, generally have this parameter, this width within their equation. However, there are old dams or farm dams without those type of information, the upstream or downstream slopes. So to avoid assumptions, equations that didn't need these items, you can use them based on the equation that we don't have all the information. So in case that the data availability is there, we really recommend to use the equations which we have that widths and slopes of the embankment in the equation. Then based on that, after just gathering everything, we said that, okay, we had a range of 20 plus 20 individual empirical equations. We just filtering and reach to top 5. We then do the round factor analysis, stepwise regressions to bring them all together to say that, okay, all of these, it seems that these are the best one. Then we use the polynomial regressions and we apply the performance criteria 3 for the magnitude error 2 based on the associations, use cross-validation and ensure that we are avoiding any overfitting. The technique here is that we considering empirical equation as individual predictors, and then outcomes of the empirical equations would be considered as an input to the data fusion based new set of the equation. So here we have used polynomial regression as a combining tools with the 5 performance criteria, 3 for magnitude, as I said, and 2 for the association. So individual empirical equations used, there are outcomes. Those outcomes is input for this combining system, and then we will have a result. Then at the end, we will have, when we got all of this information, we did some uncertainties assessments. So the final steps will be assessment. We did the 2 series of assessments were done for each breaching parameter that we have. So one based on entire outcomes to be able to compare those uncertainty and error exist in empirical equation. Then we noticed that for different parameters, the level of uncertainties and errors are not uniformly spread from low tail to the high tail of the estimation. Therefore, magnitude-based uncertainty assessment were conducted and developed and conducted to ultimately draw a confidence interval range for the estimation of the breaching parameters. So this is one example of, it's not actually an example, it's the final equation that we draw. Top one is for the linear-based regression, the lower one is for nonlinear. So for group one, if we are having a breaching parameter of the Q, peak outflow, we found out that the best empirical equations, individual empirical equations, are for Froehlich for 2016, Husha 2014, and Zhuzhang 2019. If you see that Zhuzhang is always there, and the main reason is because that is one of the few of those equations that it has a geotechnical side of things into. However, there are questions and there are challenges about how they got those erodibility component in that equations. When we use the cross-validation techniques for each iteration of training and test, we were able to calculate those 5 performance criteria that I mentioned. Therefore, for 100K of the iteration, we'll have 100K of the values, which let us present the distribution of the values in the form of histogram. When I say distribution, not probabilistic distribution, I mean just in form of the box plot or the histograms. Here are the histograms for peak outflow that you can see here. The left one are for the training and the right one is for the test stage. The blue one with the rectangular boxes for the proposed equations, and the other ones are the selected empirical equation. As you can see here for RMSE, MNE, and NE, which are the magnitude, the proposed empirical equation, the confusion proposed one is on the left, closer to the 0, in compared to the individual empirical equation. And for the association, it's more to the right, which is 1, which shows the better performance. For validation histogram that you can see on the right side, we only have the proposed equation because for those selected empirical equation, they have been originally introduced based on the result of this. So we cannot really compare their values with the validation outcomes. Instead, in addition to the calibration comparison, we also did a comparison of the proposed empirical equation and selected individual empirical equation for entire data set to be able to compare those together. Again, proposed empirical equation showed the better performance in comparison to the previous ones to some level of the degree. And the next slide, if we want to compare the uncertainty levels, what we did was we used the error percentage using for the calculation of the relative error for the breaching parameters based on that 100K for just test stage, because we wanted to ensure that we are just using the test, not the training steps. So here we can see that we found out in all of those breaching parameters, our sensitivity levels are between plus minus 300% or almost 3 order of the magnitude. When you just compare it to the literature, which is 0.5 to 1 order of the magnitudes, it shows that it's a promising outcomes. For peak outflow and the final width, the mode of the histogram leading to the 0, which is a great. While for TF, which is time of failure, we see a double peak of 100 minus 100 and another one plus 120. So this confirmed the high level of the uncertainties of the TF in comparison to the other breaching parameters. And then when we went through the details, we found that this is mostly coming from the observed data. So in the many papers, poor quality of time of failure has been reported. And when we look at the data set, we see that the time is usually in an order of like an hourly scale, 1 hour, 2 hours, 3 hours. So for example, rarely we see that they have accurately measured something like a 25 minutes, 27 minutes. Obviously, those dams are failed, people just ran and they don't even care. They don't stay there and they're looking to the watch. As I mentioned, we also observed that the distribution of errors is not uniform across the lower tail to the upper tail. So if you look into the left bottom, which says uncertainty based on the estimation magnitudes, a clustering analysis was applied to split the range and extract a simple linear regression for that range. So this has been done for all of three breaching equations. For example, within that green box that you see, we see that if the outcomes of data fusion equation for peak flow is within the range of 1,000 to 10,000 cubic meter per second, we can use this equation to go for extract the range of the estimation.
Okay. Well, just a reminder for those who have asked questions in the background, upvote those that you see. So there are quite a few of them there that may have some relevance to more than one person. So upvote those. Those are the ones that we'll handle during our panel discussion first. So keep those questions coming, and then to the presenters, if you can make sure you address as many as we can. We don't always get to all of them, but we try to address them and as many as we can. And we may also post a PDF file of the Q&A for those who are watching the recording later on. So Monty, if we can go the breach hydro bits, if we can, we'll cover some of those in our June webinar.
Yes, definitely.
And then let's so that we can get Tim on as well. If you can just give us a brief preview of what they'll see in that upcoming June webinar, and then we'll get over to Tim's. Thanks.
Yes, sure. I will go for it briefly. So what we have here is showing that what would be the main steps that you need to go one by one. And these steps are what I mentioned, that it can reach you to the level of the confidence about what you need to do. And this framework is something that you need to do to ensure that you have an objective instead of the subjective. Next slide. So there are the 5 examples that we just applied those step-by-step things, and they used HECRAS as a 2D modeling to see that if it's valid or not, and if that the range we are reaching to that level. So we can go through these practices more in that June webinar. I really like to go through that Breacher. So Breacher just developed by Forward Hydro as a very as a rapid modeling of 1,000 runs and calculate breaching parameter based on the most common recently introduced empirical equation that I mentioned. It's go and investigate through the historical database to select the closest cases. It's using the water balance to calculate each time steps. It's using the hydraulic calculation to calculate the failure. It has a 2 mode of comprehensive and manual, so you can do all of those sensitive analysis, or when you have a certain level of the certainties, you can go and extract the failure hydrograph. So if you are a two-flow person, the structure of just running is very similar to the two-flow. So you run and put your comments in the text file and the batch file are running. It have a 3 main steps of the previous empirical equation, historical data, calculation of the hydraulic, and the post-processing. So it has been already validated with HECRAS for 24 different dam breach scenarios. So it's fully reliable, and it already shows a great performance. So one of the perfect and fantastic items about the breach hydro is that breacher post processing. So it gives you ability when you're just running a comprehensive. It gives you the ability to see the plots of the existence, cloud of the plots, and the errors, and all of those can give you more information about the decision. So in conclusion, as I said, let me go for the next one. This one is about, you need to ensure that you have good information, enough information. You need to have enough knowledge. You need to know what kind of uncertainty you have for that specific cases, and then you choose the best tools that you have, and then you run it. So models can never be fully precise, but following the steps that we mentioned in our paper and this type of the tools that I mentioned here, we should be able to just reduce the uncertainty as much as possible. Sorry for passing time.
Oh, no worries. Over to Tim. What we'll do is we'll run until about the hour mark. Then we'll have a bit of a panel discussion, hit those questions that have been upvoted the most, and then we'll save some of the additional detail. You can see there's tons of it here. Additional detail for a more comprehensive webinar, 2-hour webinar in June. So over to you, Tim.
All right. Okay, so I'm talking about dam break analysis in an Australian context. If we just move on to the next slide. And so we might ask the question, what's different about dam break analysis in Australia? How is it different? Well, the answer is that it's not, at least not when it comes to the modelling, but it is. It does have a slightly different flavour because of the jurisdiction. So dams are regulated through local legislation or state-based legislation in Australia, and they define what we're going to use the modelling for and how it's going to be applied. So when we're looking at our dam break parameters and their accuracy, the requirement for accuracy is shaped by the sensitivity to decisions that need to be made by dam managers and regulators. So the way we apply dam break modelling is to assess the risk posed to the downstream community. And we might do that in one of several different ways. So we might be looking to determine a risk category. Sorry, where I mentioned risk is probability times consequence, and the dam break is focused clearly on assessing the consequence side of that about risk. So we might want to define a risk category in the classic low, medium, high variety, as can be seen in the an outtake from the ANCOLD guidelines in the table on the right there. Or alternatively, we might want to assess the risk algebraically in the form of a loss of life versus probability chart of the form which we have on the lower right. And we may also be looking to potentially characterise the flood progression or the flood inundation for emergency planning. Specifically, when it comes to the Australian approach, what we're finding is there are some themes that are emerging in that there's a reducing appetite for risk, which is leading to potentially substantial upgrade costs, and also applying dam break analysis to some very small dams, as low in some cases as only half a metre high. So what does all this mean in practice for the dam break parameters? Well, one way of looking at it is to say dam break parameters matter. There's a fair bit of variability in those parameters. The times and the widths can vary by factors of double or triple. The outflows can vary by orders of magnitude. So it means we want to try and get those estimates as accurate as we can, so we can make appropriate decisions on investments. But then again, maybe they don't matter that much, depending upon the application. So what's the sensitivity of the parameters? So the inputs can vary substantially, but the investment decisions aren't made based upon the input parameters. They're made based upon the outcomes from our analysis. So what we really need to do is to try and understand the importance of those parameters relative to our overall outcomes. So we can see here, if we're doing a sensitivity analysis, that there's a progression. So the aim of the analysis is not actually to assess what the dam break parameters are. I mean, that's a step on the journey. Our aim is to accurately, or as well as we can, assess what the risk is so that we can make appropriate decisions on our dam in relation to our dam assets. So we may have dam break parameters which can in turn be used to produce a dam break hydrograph, and it's most obvious where we've got our the impact of the dam break parameters on the dam break hydrograph. That in turn then is used to produce put into a hydraulic model, produces a flood inundation map, and we use those as a basis for assessing what the consequences of the breach are in terms of dollars and life safety. And that then is used to assess where we sit in terms of our the consequence component of our risk. So what we really want to understand is how do the dam break parameters affect our risk category, or at least the consequence component of that. And understanding the variability of those parameters in context is important, because we may find that, as we go down that list, there might be something else which is having an equally great impact upon our outcomes. And I'm looking at you, life safety. There's some pretty substantial leaps of faith we make when we assess a number of aspects of the life safety. So the dam break parameters may not even be the most critical component in producing our outcomes. So we want to try and understand that. But one of the things we do have going for us is that the dam break parameters, while they can vary substantially, when it comes to a risk category, we may find that the parameters we're using that we're looking to estimate to determine that risk category, they may also be order of magnitude scale before we move into different risk categories. For example, the loss of life component of that risk chart that I was showing before, that's on a logarithmic axis. So the other important component to recognise is that it's okay not to know the answer. We do have to provide a recommendation to a client, but they will often appreciate us telling them that, look, here's what we're going to provide as our best estimate, but it can vary, and it allows them then to make an informed decision. So we're going to the next slide. So I've just got a graph here from an example where we found that the outcomes weren't particularly sensitive to the modelled input parameters. It's a particular case, an interesting one, where we had a dam that was built in the 20s. It failed, and then it was rebuilt, and we had a data point from that failure where there was a flight mark from the failure at the township, the key township, downstream by about 4 kilometres. So the dam height at 27 metres, volume 3,500 megalitres. It was a concrete face rockfill, so the bridge time is likely to be quite rapid, and we varied the model width. The difference in elevations, which we've got shown on the graph there, was about 3 metres close to the dam. But by the time we got down to the point where we had the majority of our consequences down about 4 kilometres downstream, it had settled down to about 0.4 metre differential. The max, probably the best accuracy we could hope for in relation to the estimate from our actual data point would have been plus or minus half a metre. So the difference in those parameters did end up having an impact upon our overall outcomes, which is a very comforting position to be in when we're reporting back to the client. An alternative may be a case where that doesn't occur, and we have to we find that the outcomes are sensitive. So let's say it might have been a bit further back up in the further upstream. So in that case, we may recommend to the client that they focus a little bit more then on trying to get a better representation of what that breach width might have been. So the key message is that breach flow is a highly uncertain procedure, but we inoculate ourselves against that all we can by doing a sensitivity analysis so that we can understand exactly how those parameters affect our outputs, and then we want to make sure that we communicate that as clearly as we can to the client so that we can allow them to make an informed decision when it comes to their investments.
Excellent. Well, as you see, there is a ton of content to get through. That's why we mentioned at the beginning that we'll keep the content here to the hour and then run a bit past that with our Q&A discussion. But do keep in mind that if you sign up for that link that we've provided in the chat, we'll have 2 hours with you to give a introduction to dam breach modeling, which will then feed into specific courses in specific software for anybody who wants to try that. So if you can all turn your cameras back on, what we'll do is just go through everybody, let you pick one question, and rather than just going around again and having closing remarks after that, we'll just have everybody address the most prominent or most pertinent question that you've seen in the Q&A. And then we'll hear more from you in our next webinar. Let's go. Let's hear from Kyle. We haven't heard from you yet. Kyle, you want to pick something out and then just give people a little bit of a preview of what's coming when we get into more detail.
There was a lot to take in.
Yes.
It's our experts that presented today. The question that stood out to me, there was one from Angus who was asking if we're using probabilistic models for historical failures and breach parameters and we don't have enough data, what model should we be using? I think Monty touched on it very briefly at the end. It was part of the inspiration behind the whole breach hydro moving across into water balance modeling. So at least my view after the last few years and all this numerical modeling and the papers and things, we need to do a lot more simulations to have confidence in the results that we're presenting, especially from an engineering outcome. I'm not sure if the hydrodynamic modeling is the right approach because it's computationally time-consuming and I guess expensive for the broader client or the consultant. So water balance modeling is a bit of a proxy to try to get around that. Angus asked, if we don't have enough data, what model should we be using? What parameters should we be using? At least my view is to use the empirical equations and to try to use the more recent ones. As Mayara talked about briefly, the older equations are more out of date because there might not be as good data or the analysis might be out of date as well. Though Froehlich's more recent papers and equations obviously would supersede his previous equations. Ideally, what we should be doing is using those empirical equations to get a rough estimate of what our feasible breach parameters should be and performing that broader probabilistic approach and try to determine what acceptable range of parameters would make sense. And then I guess at the end, in a perfect case, if you have the time, you would want to have historical dams to reference against. So I'm going to dig through that massive database Mayara put together because it looks very impressive. But we can do the analysis, defend the equations with recent, relevant, good quality. Froehlich talked about good quality data sets that were pulled out of newspapers. You can do all of that and then demonstrate the parameters we chose are feasible and here's a historical breach equation. Then that seems to be the most defendable results and most defendable in terms of distributions we might pull out in the end. Instead of choosing the median peak flow for our design failure event, maybe we want to choose something towards the 90th percentile or the 75th percentile because it's high risk. So we've done all of that, at least we can have a more defendable result. A bit of waffling on that question from Elliot. I hope that covered it.
Yeah, and I hope, so again, have a look at the written responses. Kyle, again, thanks for getting this group together. And if Kyle being a CFD modeler too, and has helped out with some of those in the past, we will get into 3D modeling. And there have been some questions in the background about 1D versus 2D versus 3D. When we get into tailings dams, we're going to show you some things in Flow 3D and other CFD models where we start varying the looking at non-Newtonian parameters.
That premium webinar as well, we'll do our best to talk about engineering application and obviously we won't make it software specific. There's great tools out there, Breach obviously, and 2Flow and Mike tools and Ugo, all sorts of things, but like trying to work on the best practice engineering approach.
Yeah, we'll try and get everybody covered. The next session will be non-denominational, and then we get into some specific ones for individual software packages after that. David, if you could let us know, people you've used the Froehlich 95, a Froehlich 2008. Is there going to be a Froehlich 2024, or will future generations refer back to a 2030, a 2050? Is there something else coming? And then if you have any other questions, maybe pick a question out of the ones that have been asked that you wanted to address here live.
Well, I continue to collect data as they become available. I'm always looking I'm no longer going out and measuring dam breaches on my own. So I look for other published information. Occasionally I find something. If anybody has some original data that's well documented and want to share it, I'd be glad if you would send it to me. So I've been looking at neural networks recently, and there'll be some nice things coming in a future journal paper. So evaluating estimated values and uncertainties. Again, neural networks, one must be really careful making sure you're not predicting nonsense. So you need to run what are called profile traces.
Well, if things
but you put this all in an Excel spreadsheet, you enter a few numbers, and then you have everything printed out right there.
Yeah, perfect. Well, maybe future generations, we'll you can go retire, and then we'll have an AI version of you answering all these questions that'll be filled with all of your publications. So we'll see where we go from here. Mari, anything you wanted to hit? Any question that you wanted to grab from the ones that you've addressed in the background?
Yeah, but I tried to address some questions that were for me, but sorry, you can't reach me outside of this presentation. But overall, I have seen if probability will be available. Overall, probability, it's the results of my PhD work. So if one day I found pertinent to put it there, and maybe, but I will need a host. So overall, I will see how I manage that. But it's not right now. But the user manual is included in my PhD thesis. And if not, I have seen different questions related to the model use, the deterministic model, considering the time calculation. So overall, using a simplified dam breach model evolution versus an ECRAS that includes the storage influence, the downstream influence, of course, results in more time calculation and less probabilistic scenario for that same time. So this is, again, it's for engineering in practice, how we manage precision and time calculation is still here an issue. And I think it will be, if we're talking about probabilistic, artificial, or deterministic modeling. And of course, empirical is was the first answer of this, capture these uncertainties. But now that we have tools, more knowledge available, I think that we might start investigating other models.
Well, thanks. Yeah, thanks for sharing all of that background information. It looks like a great deal of research going on. We will post as much of that as we can through the links on the YouTube channel and in the description, and also along in those accompanying websites. Let's see. Let's get a question from Monty, and then we'll have Tim bring it home for us.
Yeah. For me, I have noticed that there are some concern about the Zhu-Zhang equations. Some people ask that why you have put it there, because we've seen that there have been some level of uncertainty, some level of they are not sure about the way they choose it. And so first thing is the methods of the data fusion is objective, is not subjective. We don't put it ourselves. We go through all of those filtration process from step one to another steps, and the system selecting based on the most available equation that we have. And then we have that combination of those equations, and the rate that the system gives depends on the level of the reliability counts. For example, if you look into those equation and numbers, you see that, for example, for the Froehlich ones, it comes the higher the slopes. However, I think it's very important to have at least one single empirical equation which brings the geotechnical side of components as well, because dam break is not all about the hydraulic. It's not all about the water level of the water, other things. We need to see some other things like additional compacts, something like a safeties. And these components all together go through the erodibility situation. I can remember the first time that we received some feedback from David. He actually mentioned about the concern about how they got those erodibility values, and we understand, appreciate those. And we have put in our paper about our concern as well about those bonds, but it's still the time that another equation comes with the level of the certainty about the geotechnical side of things, this is what we can use it and we can apply. Then if the new version of or another equation with the geotechnical side of it comes, we can just replace and go through a step 1 to a final step again and bring a new equation. Data fusion is about approach, is not about those numbers. So you can just redoing based on the new information and based on the new set of empirical equation.
Sounds good. I think that's where we're heading. That's where the industry's going, and we want to make sure we bring you the most relevant, most recent, most innovative content we can, because this is where we're all heading as an industry. Tim, bring it home for us.
I don't have there are a couple of questions which are probably more related to consequence assessment and downbreak. But I'd say, look, there's some excellent tools here, but, you can go down the rabbit hole, trying to investigate these things. But the tools are really useful. But, I think it's probably just a matter of making sure that we pick and choose when we're going to apply it. So when do we need to make sure that we really need to focus in on those? And it all depends upon, like I was saying, in the application. So if it's not having that great an impact upon the overall result that our client needs, well, then, we can stick with something simpler. But as it starts to have a greater and greater impact, well, then let's start making use of these tools and apply them.
Perfect. All right. Well, you'll see some links here. We'll bring up some slides. If you do want more of this content, if you want to do this yourself, if you want to start modeling yourself, whether it's Monte Carlo runs, 2D runs, 3D runs, or, just a 1D simple spreadsheets and things like that. We are going to look into the black box of these things going forward. For those who had to run early, everybody's going to get a recording link. So do contact us in the background and let us know if there's further questions that you'd like to see addressed and what kind of content you want to see going forward. We do have next week's webinar on HydroGPT coming up, and then this Dam Breach Essentials course, which is a 2-hour session with some of the same presenters where we get into more detail than you were able to see today. So thanks so much for our presenters for joining us. Been an honor to be with you and to be involved in this very important work with you here. And we look forward to seeing you next time with the Australian Water School. We'll see you later.